Unit 1, Notes 1.4. These are the notes for Unit 1, Day 4. Inverse functions. Let's start talking about the inverse. Looking at this relation right here and this relation right here, what do you notice in these two mappings? If you said that you noticed that the domain and range switch, you'd be correct. And that's the whole main idea of this lesson. If you can remember to form the inverse, I switch the x's and y's, or I switch the domain and the range. If you can remember that, you've got this lesson. Now, looking at the relation, is the relation a function? And if you wrote it out in coordinate points, you'd probably say, yeah, it is, because the domain doesn't repeat. The x's don't repeat. But look at the inverse. Is the inverse a function? And you'd probably say no because, well, 1 and 2 both do the same thing. 1 goes to 1.2, but it also goes to 1.4. So while the relation is a function, the inverse is not. And that is totally okay. That is perfectly okay. One can be a function, the other one might not be. Or the relation might not be and the inverse is. They both don't have, it's not an all or nothing deal. So let's talk about the main ideas in proper terminology. So the inverse of a function is denoted by f-1, but we don't say f-1. We read it as the inverse of f, the inverse of f. Now, occasionally somebody might say f inverse, and while that's correct, I'm going to be honest, I haven't heard hardly anybody call it f inverse. It's always read as the inverse of f. Now, while we use f of x to denote functions, the relation, the inverse of f of x, may or may not be a function. And that's what we talked about up there with the relation is, but the inverse wasn't. Well, how will we know if the inverse of f is a function? How do we know? Well, same way we know if f of x is a function. Do the x's repeat when you form the inverse? Is there, for every x, there's only one y? Does it pass the vertical line test? So we can still use the same tools that we use on the original function. We can use those on the inverse function as well. Now, let's talk about one-to-one functions. Now, before you go write down all this math mumbo-jumbo, the one thing I want to call your attention to is a one-to-one function. Okay? For it to be a one-to-one function, f of x and the inverse of f must both be functions. Okay, so if you want to ignore all the math mumbo jumbo up front, for a one-to-one function, both the original and its inverse must both be functions. So the original has to be a function and the inverse has to be a function. If both are not functions, it's not one-to-one. Well, you're probably wondering, well, in terms of x and y, what does that mean? Well, for it to be a one-to-one function, x does not repeat, but also y does not repeat. Because think about it. In the original function, the x becomes the y and the y becomes the x. So if x doesn't repeat, then that means in the inverse y is not going to repeat. And if the y doesn't repeat in the original, that becomes the x of the inverse and it doesn't repeat. So that's the main thing you need to remember, is that they both must be functions, and in essence, when you're looking at the original, neither x nor y can repeat. So let's talk about how we find and graph inverses. So when you see this notation right here, f-1 of x, that simply means find the inverse of f of x. To do that, we're going to switch x and y and solve for y. So let's talk about this. If you're given a table of values that you graph and it says find the inverse, all you've got to do is switch the x's and y's in the table, graph that, and you've graphed the inverse. If you're finding it algebraically, you switch the x and y in the equation, and then you resolve for y. Now, we do have a test to determine if I'm given two functions to determine if they are inverses. And the test that I'm going to use is this. If f of g of x equals x and g of f of x and g of f of x equals x. So if when I take g of x and I plug it into f of x, if I get x, and then if I get f of x and I plug it into g of x and I get x, if I get x on both of those, then we know that they're going to be inverses. Now, they quite legit have to both equal x. Okay, so if you get f of g of x equals 2 and g of f of x equals 2, they're not inverses. So when I take g of x and I plug it into f of x, I need to get out a single x. Same for when I take f of x and when I plug it into g of x, I get x as well. Okay, so we're actually going to look at this so that way you're not like wondering, well, what is she talking about? But I do want to tell you this. When we ask you to test if two functions are inverses, that does not mean take one, find the inverse, and go, oh, look, they're the same. That's not what we mean. If we tell you to determine if these two functions are inverse, you have to complete this test. If you don't complete this test, you are not going to get credit. It's that plain, that simple, that cut and dry. You have to know how to perform the test to see if they're inverses. Okay, let's look at our example. Given f of x is equal to 1/2 x plus 8 and g of x is equal to 2x minus 16. I want us to find f of g of x. Now, if you'll recall, g of x is 2x minus 16. So that means I'm going to take 2x minus 16, and anywhere I see an x, I'm going to plug in 2x minus 16. Now I distribute. So half of 2x is x, half of 16 is 8. So I have x minus 8 plus 8. Check it out. They cancel, and I get x. But just because I get one doesn't mean the other will produce a similar situation. So let's try the other one. So now I want to find g of f of x. So remember, this is going to be, well, f of x is 1/2 x plus 8. So that means anywhere I see an x, I'm going to plug in 1/2 x plus 8. So 2 times 1/2 x plus 8 minus 16. You can't forget that ending part. You're just subbing in for x. So 2 times 1/2 is 1, so x. 2 times 8 is 16. So x plus 16 minus 16, they cancel out, and I got x. So since I both got x, I know they are inverses because f of g of x equals g of f of x, which is x. Now, if I asked you to find g of f of 4, all I have to do is take this 4 and plug it in there, and I get 4. If I ask you to find f of g of 1, 2, 3, 4, 5, then you're going to take 1, 2, 3, 4, 5 and plug it in up there and get 1, 2, 3, 4, 5. The point we're making with this is that if you know g and f are inverses, whatever x you plug in, because it equals x, whatever x you plug in, you're going to get the same answer right back. So it's kind of like g and f kind of undo each other, and they're like, see ya, and you're left with 4. Let's look here. We're given x and y. So the first thing I'm going to do in this table of values right here is I'm going to plot those 4 coordinate points. So I plotted -1, 1. I plotted 0, 2. I plotted 1, 3, and then I plotted 1, 4. Now, if a relation or function is described by x and y, what can we do to the x and y to get the inverse? If you said switch, you'd be correct. So I'm going to take the table at the left, and all I'm going to do is switch x and y to get the inverse. So now I'm going to graph 1, negative 1, 2, 0, 3, 1, and 4, 1. And you'll notice here they kind of look like magnets and they're repelling each other. Kind of also looks like a butterfly, but you'll notice when that happens, when it looks like they're kind of repelling each other in the same shape, guys, that's all that is a reflection over the line y equals x. And that's one thing you always want to remember, is that the inverse of a relation is a reflection over the line y equals x. Always. It doesn't matter what you're reflecting. The inverse of a function will always be the reflection over y equals x. Okay? So let's talk about the x-intercept and the y-intercept. So here, we don't really know, our x-intercept, but I do notice we have a y-intercept. But check it out. The y-intercept of the original becomes the x-intercept of the inverse. Same with if we know the x-intercept of the original. The x-intercept of the original will become the y-intercept of the inverse, because remember, all we're doing is switching x and y. All right, let's look at our last example of Unit 1, y'all. Congratulations, y'all made it all the way through to the end of your very first unit in Algebra 2 Pre-AP. Kudos to y'all. So what this problem wants us to do is we are going to find the inverse of this linear function, and then we're going to graph both lines. So let's just jump ahead and let's go ahead and let's graph this line. So the first thing I'm going to do is I'm going to start at the B, the y-intercept of 4. I'm going to go down 2 over 5, down 2 over 5. Now, if you wanted to get a more precise line, you could have gone back to the intercept and gone up to left 5, up to left 5. You'd still get the same line. So there's our f of x. Now, here's what I want you to remember, okay? F of x and y, f of x and y are the same thing. So before you start flipping any x's and y's, you need to change f of x to y. That's one of the most critical important steps. Okay, so remember, to find the inverse, we switch the x and y, and then we solve the equation for y. So I am going to switch x and y's. Now, I have to resolve for y, which means, first of all, I need to get this term by itself. So I need to subtract 4 from both sides. Sweet. Okay, now, how am I going to get rid of multiplication by negative 2 over 5? Well, I'm going to multiply by negative 5 over 2. So I multiply both sides by negative 5 over 2. So another way you could have done it is multiplied everything by 5 and then divided by negative 2. You'd get the same response. Okay, so negative 5 over 2x is negative 5 over 2x. But when I take negative 5 over 2 times the negative 4, which is technically over 1, I get positive 20 over 2, which is 10. And so that's how I come up with negative 5 halves x plus 10. Okay. So now I'm ready to graph that line. I start at 10, I go down 5 over 2, down 5 over 2, and connect the dots. Now, if you're still not sure, you're like, well, is that really a reflection? Well, let's look. Here's the line y equals x, and let's look here. So this guy right here, he reflected over and became that guy. So that works. And then let's look at this guy and this guy. He reflected over to become this guy. So they worked. They're both pieces of the lines are reflection over the line y equals x. Now let's talk about our x and y intercept. So if you look at the original here, you'll see that that point is 0, 4. So the y-intercept of the original was 0, 4. But let's look at the x-intercept of the inverse, and look, it's 4, 0. So yeah, the y-intercept became the x-intercept. It works. You could also check up here and go, well, the y-intercept of the inverse is 0, 10. Whoops, I apologize. Let me try to write that again. It is 0, 10. And then if you look down here, this is 10, 0. So yeah, the x-intercepts and y-intercepts flip-flop as well. Let's talk about domain and range. Now, if you remember all the way back to like day one, what did we talk about the domain and range being? The domain and range of a line are always negative infinity to infinity. Well, guess what? You also flip the domain and range, which in this case, they're both negative infinity to infinity. So it works. Now, are they both functions? Are they both functions? So let's erase all my writing on the graph. So are they both functions? Yeah, they both pass the vertical line test. So if they're both functions, is it a one-to-one function? It sure is. It's a one-to-one function. All right, so this concludes your very last unit, that's not even a word. This concludes your very last unit lesson of Unit 1. All right, so we are done with Unit 1. Next class period, we'll talk about starting to do a review, get ready for a test and all that stuff. But congratulations for hanging in there and closing out your very last lesson of Unit 1. Have a great one, guys.